Hello, chemistry world. It's Tuesday, April 5th. Let's take a look on page 410. Right in the middle of page 410, above the green table, you see like dissolves like. We talked about that, but I'm going to go ahead and read that last sentence before the green table. It says, what makes substances similar depends upon the type of bonding, the polarity or non-polarity, and the intermolecular forces between the solute and solvent. So I showed you cornstarch and water didn't mix. And I'm going to now show you another one that is not a good mix, and that's salt and oil. So here's the oil, and here's the salt. We'll go ahead and stick that solvent, oil in there. That'll be the solvent. Okay. And then we'll go ahead and stick some salt in there. So you'll see it doesn't even think about dissolving. It just goes right on through. Actually, it just plops right down to the bottom. It looks like it expands or it grows or something anyway. Shake that back up again. And it's just like one of those globes at Christmas time, isn't it? Falling right back to the bottom. It's not dissolving, just caking up. Salt and oil do not mix because salt is an ionic substance and oil is a non-polar solvent. We need a polar solvent. What can you think of as a polar solvent? How about water? We get water in there, what's going to happen? You have any idea? Of course, you know what's going to happen. The oil is going to rise to the top, and the salt water is going to be on the bottom. You have to give it a little bit of time, and that salt will dissolve in the water, which sits on the bottom. It's probably in improper proportion right there because I didn't. Okay. Go over to page 411. Let me show you something here. You have any idea what that is? It's what they pack with your electronic equipment or your shoes to keep the material dry inside the package. Here's a bigger example of the same thing. It's called a desiccant. And the word desiccant has two C's and one S. Two C's and one S. What's with that? Anyway, that's the way you spell desiccant. Now, where did desiccant come from? I'm on page 411. There are certain materials which, when you dissolve them in water, they grab water molecules as they dry out. Let's say the definition right here for hydration. The solution process with water as the solvent is referred to as hydration. I'm on page 411. So when the coach tells you to remain hydrated, he wants those electrolytes dissolved in water, doesn't he? And he wants the hydration. And so the ions that break apart are hydrated. What does that mean? They break into ions and they tuck in between the water molecules. They're hydrated. Now, as that solution evaporates the water, then the ions come back together again. And there are certain crystals that might form. And those crystals sometimes grab the water molecules and will not let them go up into the air as water vapor. When it evaporates, a slow process, it forms what we call hydrates. Hydrated compounds. Copper 2 sulfate is example down on page 411. Copper 2 sulfate. I'm going to use red because I would like to refer back to what I had in yesterday's lesson. Copper 2 sulfate looks like this. CuSO4. Sulfate is -2. Copper 2 is +2. So copper 2 sulfate, crisscross, leave it alone. Now, when you go ahead and you write the compound that results when there's a slow evaporation of a copper sulfate solution, let's suppose that there's rain and it flows down through the rocks. And the rocks have some copper and some sulfate. Well, the rain kind of like pulls those ions together and forms the copper 2 sulfate, but then it also has these water molecules so close to the ions, since it's hydrated, that when it evaporates, they cling to some of these water molecules. And if you take a look on the bottom of 411, you're going to see that there are 5 water molecules that are attached, 1, 2, 3, 4, 5, that are attached to every copper 2 sulfate formula unit. Is it copper 2 sulfate? Yeah, it is. Okay, so what we do is we put a raised dot and we say 5H2O. And the way to say this word is copper, Roman numeral 2, see, sulfate, and it is hold on. I'm trying to make sure I spelled sulfate together, and I thought I spelled it wrong. I don't want you to go to college messed up. This means penta. And this means hydrate. So the way to say that compound, which is a hydrate, is copper 2 sulfate pentahydrate. Now there's a way, and I think I showed this to you earlier in the year. There's a way to go ahead and drive off this water. And that is simply to put a flame on it. And it might change color when you do. These packets are dehydrated, typically silicon gel. It is silicon dioxide, SiO2. And one water molecule, I guess. And those are like what they do. What they do is they package this in here, and it's very dry because they pack it without the water, but it wants the water, and so it absorbs the water vapor that's in the box, and your shoes stay nice and dry. And so this is called a dehydrate, or you might call it an anhydrous compound because there's no water attached. But then it pulls it in from the air, and then you get a hydrated compound like this, copper sulfate pentahydrate. Okay, and another example is plaster of Paris. Another example is gypsum. They all act like sponges and pull in water molecules, dry sponges. Okay, so you might have to name one of those, who knows. Desiccant packets. On the bottom of page 411, I want you to read this with me. Ionic compounds are generally not soluble in nonpolar solvents, like carbon tetrachloride, CCl4, and toluene, C6H5CH3. The nonpolar solvent molecules do not attract the ions of a crystal strongly enough to overcome the forces holding the crystals together. What would you expect lithium chloride? Would you expect lithium chloride to dissolve in toluene? No, because lithium chloride is ionic and toluene is nonpolar. And they just vary too much in bonding polarity and intermolecular forces. That takes care of page 411. Go back to page 412 with me for a second. You're going to see that lovely Lewis structure there in the middle that I drew up here in blue during our last lesson. I want to revisit this. Do you know that there is a name for this group right here? It's called a hydroxyl group. It's called a hydroxyl group. Now, what's the difference between a hydroxide, which is OH, and a hydroxyl, which is OH? Well, the difference is, let's take magnesium hydroxide. Is the hydroxide attached to a metal? And let's take this hydroxyl group. Is it attached to nonmetals, carbons and hydrogens? That's called a molecule. That's called a formula unit. Please go to college knowing those words. Molecule, formula unit, C2H5OH. And on alcohols, there's always a hydroxyl group on the end. While the hydroxyl group is polar, it has a positive end and a negative end. It makes it dissolvable in water, because water is also polar. They're likes. And so it makes them miscible. Well, I call it mixable. It will dissolve in water because of that little hydroxyl group, but it will not form ions in solution because this does not detach from the molecule. The molecule stays intact as it dissolves in the water. The bonds of attraction are too strong right here, those covalent bonds, to pull it apart. Okay, I think that's enough for us to talk about today. We'll go ahead and do page 413 tomorrow. See you.